All right, here we go, guys. We're going to focus on ratio tables today. This is RP.3a, and this is the first part of our last standard before our unit test. So let's dive right in. So today our learning target our learning targets are that I can find the percent of a number as a rate per 100. I can solve percent problems, and I can divide fractions by fractions. So at any point in time during this video, if you need me to slow down, just pause. You can rewind. Just make sure that you are writing down any questions that you have so that you can bring it to me or bring it to your teacher the next day. So let's talk about equivalent ratios. Well, what are they? Well, equivalent ratios express the same relationship between two quantities. So what does that mean? Well, quantities, for one, is just a big word that means number of items. Okay, so if we're talking about expressing the same relationship between two quantities, we want to focus on, so let's focus on fractions. In 5th grade, you focused on fractions and you focused on making equivalent fractions. So let's review that. Let's say I have 1/2. This 1/2 can be drawn this way. Excuse me. I have a whole piece of something. Let's say this is a Hershey bar, and I split it up into 2 equal parts. Then I'm going to shade this top part. This is an example of 1/2. But now if I multiply, or if I try to make an equivalent fraction, let's multiply the top number by 2 and the bottom number by 2. Then 1 times 2 gives me 2, and 2 times 2 gives me 4. I've just created an equivalent fraction, meaning that these two fractions, 1/2 and 2/4, are the exact same quantity. So 1/2 transformed into 2/4. Let's see if they cover the same space. So I take the same Hershey bar. Okay, it's not drawn accurately, but you get the picture. So I take a Hershey bar and I cut them into 2 equal pieces, but instead of 2 equal pieces this time, I want to cut them into 4 equal pieces. So the bottom number always tells me how many equal parts to cut something into. So in this time, instead of shading 1 part, I'm going to shade 2 parts. Excuse me. So if we look at both of our drawings, we can see that they both cover the same amount of space. So these fractions, 1/2 and 2/4, cover the exact same amount of space, or the same amount of space. So we want to focus our attention on equivalent fractions for the duration of this topic. So let's move past this. It just says the ratios 1/3, 2/6, and 3/9 are equivalent ratios. I want you guys to pause the video and try to figure out how did they get from 1/3 to 2/6, and how did they get from 1/3 to 3/9. Now from 1/3 to 3/9, we multiply this by 3. So whatever I do on the top, I do on the bottom. So 1 times 3, excuse me, gives me 3, and 3 times 3 gives me 9. And how do I get from 1/3 to 2/6? Well, 1 times 2 gives me 2, and 3 times 2 gives me 6. So as long as I multiply by the top number by the same number, multiply the top and the bottom by the same number, then I'm making equivalent fractions. That whole process of multiplying or dividing by the same number is going to be called our scaling, which we'll talk about in the future or coming up. So what's a ratio table? A ratio table organizes ratios into columns that are filled with pairs of numbers that have the same ratio or are equivalent. So basically, all this says is that we have equivalent fractions that are wrapped up in boxes. So let's take a look at what an equivalent or a ratio table looks like. Excuse me. So we have this example of cups of oats compared to the quantities of oatmeal cookies. So in this ratio table, we focus on this 1 cup of oats can make 24 oatmeal cookies. So if 1 cup of oats can make Excuse me here. Apologize about that. So if 1 cup of oats can make 24 oatmeal cookies, then how many cookies can 5 cups of oats make? So these are just like fractions. So right, this is 1 over 24. These are just like equivalent fractions, but they just have boxes around them. So how do I get from 1 over 24 to 5 over something? So you ask yourself, well, 1 times what gives me 5? Well, 5. So whatever I do on the top, so I multiply this by 5, then I must do also the same on the bottom. So 24 times 5 gives me, I'll pause so you can pause the video, try to figure out what is 24 times 5. Now 24 times 5 will give me 120. So we talked about this concept of scaling before. Now this is exactly what we were doing up until this whole time, multiplying or dividing two related quantities by the same number. Okay, so sometimes we may need to scale back, and then sometimes we may need to scale forward. So always remember that if you are scaling back, we are dividing, and if you are scaling forward, then we are multiplying. For example, if I have the fraction 3/6, if I need to scale forward, then I'm going to multiply by some number. So 3 times, let's pick a number, let's say 7. Well, 3 times 7 gives me 21. Whatever I do on the top, I must also do on the bottom. So 6 times 7 gives me 42. So now I have just created an equivalent fraction or equivalent ratio by multiplying or scaling forward using 7. Now let's talk about what would happen if I scaled backwards. Well, when we scale backwards, we must divide. So we need to figure out what number does 3, or what number goes into 3 and 6, or what are some common factors for 3 and 6. So I can divide both 3 and 6 by 3. So 3 divided by 3 is 1, and 6 divided by 3 is 2. So now I have just scaled backwards, and now I have 1/2. So this is the concept of scaling. So let's continue. Now here's an example where scaling back and scaling forward are very important. So it says a department store has socks on sale for 4 pairs for $10. Use the ratio table to find the cost of 6 pairs of socks. So what we have here is an example to where I cannot effectively multiply by a whole number to get to 6. So I need to use some strategies of scaling back or scaling forward. So since there is no whole number, like I said, by which you can multiply 4 to get 6, instead we scale back to 2 and then forward to 6. Well, Mr. Golden, what does that look like? So let's take a look at what that looks like. So down here on the bottom, I knew I couldn't get from 4 to 6. So I said, okay, let me just scale back so that I can see what I can work with. So 4 divided by 2, and the reason why we use 2 is because we were really just trying to figure out what is a common factor between 4 and 10. And since I know that 2 also goes into 4 and 10, then I can divide them by 2. So 4 divided by 2 gives me 2, and 10 divided by 2 gives me 5. So now I can really go from 2 to 6. So this is what this line up top is for. So this line tells me I can go from 2 to 6. So see, the goal is to try to move from a number that you know. So here's 4, this is a number that we knew, to our end goal, which is 6. And since I couldn't do that, I needed to scale back by dividing to a number that I could work with. So 4 divided by 2 gives me 2. And now I know I can go from 2 to 6 by scaling forward. So 2 times 3 gives me 6. And whatever I do on the top, I need to also do on the bottom. So 5 times 3 gives me 15. Excuse me. So that means that if I needed 6 pairs of socks, I would pay $15. So now, here's our second example. What I want you to do is use what we learned in the first example to solve this one. So go ahead and pause the video now and take a minute to solve this one on your own. So now, here's how we solve this. Christine is making fleece blankets. 6 yards of fleece will make 2 blankets. How many blankets can she make with 9 yards of fleece? So I can't effectively go from 6 to 9. There's no whole number I could multiply by to give me 9. So let's try scaling back. So I have to ask myself, well, what can I divide 6 and 2 by to get an even or to get a whole number? Well, I take a look at my factors, okay? And a factor they have in common is 2. So 6 divided by 2 gives me 3. So whatever I do on the top, I need to do to the bottom. 2 divided by 2 gives me 1. So now that I have this, I have 3 over 1. I can now go from 3 to 9 because I know that I can multiply 3 by 3 to give me 9. So whatever I do on the top, I need to also do on the bottom. So 1 times 3 gives me 3. Okay. Apologize about that, guys. So we have 1 times 3 gives me 3. So that means that I have 3 blankets that come from 9 yards of fleece. So let's try another way to get this, because there are many different ways to solve this problem. So instead of scaling back, let's try to scale forward and see if we get the same answer. So let's try to go from 6 to a number greater than 6. So let's do 6 times 3. 6 times 3 gives me 18. So whatever I do on the top, do on the bottom. 2 times 3 gives me 6. So how can I go from 18 now to 9? Well, this is easy. I just scale back. So 18 divided by 2 gives me 9. Whatever I do on the top, do on the bottom. 6 divided by 2 gives me 3. So we get the same answer. Let's try one more strategy. So I see that 6 and 2 are compatible numbers. So let's see. 6 divided by what gives me 2? Well, 3. 6 divided by 3 gives me 2. So whatever I do on the left, let's try to see if it works on the right. 6 divided by 3 gives me, or 9 divided by 3 gives me 3. So there are many ways to do this problem. The one thing you want to focus on is to focus on ways that you can scale forward and scale back to work for you. For example, one thing that some students make mistakes on, they scale forward or scale back to a number that still doesn't work. So if I were to scale from 6, let's say I want to scale up 6 times 2 gives me 12. So multiply whatever I do on the top, I do on the bottom. Well, 2 times 2 gives me 4. Now I want you to take a minute and think about why this scaling forward would not help me get to my end goal. Now, the reason this doesn't work is that I still can't get from 12 to 9 using a whole number for multiplication or division. I would have to continue scaling. I would have to continue scaling forward or backward to get to my goal. Now, it can be done. It's just going to take some extra work. For example, I can go from 12 over 4. I can multiply by 3 and get 36. And multiply this 4 by 3 and I get 12. And then I would go from 36 back to 9 by dividing by 4. And then 12 divided by 4 still gives me 3. Now it was more work, but still works.